Okay, so we will be learning about the Schering bridge. So Schering bridge is commonly used is bridge, and it is used for measuring the capacitance of a capacitor, dissipation factor, and other parameters. It works on the principle of balancing the load on its arm. So we can have a look over the circuit diagram of Schering bridge. We can see that there are four arms: AB, BC, CD, and AD. So in the AB arm we have two components, C1 and R1. C1 is the unknown capacitor and R1 is a series resistance representing the dielectric loss in capacitor C1. In second arm, which is BC, we have R3, a non-inductive resistor. In third arm, we have C and D, we have two components parallel to each other. One of them is the capacitor C4, which is a variable capacitor parallel to R4, and R4 is a variable non-inductive resistor. In the last arm, we have A and D. We have only one component, which is C2. So C2 is a standard capacitor. So we can see that in each arm there is a total impedance represented with a Z1, Z2, Z3, Z4 for arm AB, AD, AB, BC, and CD respectively. So as mentioned before, the Schering bridge works on the principle of balancing the load in the arms. So balancing is obtained by varying the R3 and R4. So based on the circuit diagram of the Schering bridge, we can obtain the balancing condition as Z1 times Z4 is equals to Z2 and Z3. So when the product of Z1 and Z4 is equals to the product of Z2 and Z3, at that condition our Schering bridge seems to be balanced. So from the circuit diagram, in the arm A and B, we can see that there are two components, capacitor C1 and resistors R1. So based on that, we can have the total impedance as R1 plus 1 over j omega C1, as they are in series. So we just need to add the resistance and the capacitance, and we know that the capacitance of a capacitor is represented with the formula 1 over j omega C1. So that's why we have Z1 is equals to R1 plus 1 over j omega C1. Now moving on to the another arm, which is A and D. So we can see that in A and D we only have one capacitor, therefore the total impedance will be the given by the total capacitance, and the capacitance is been denoted or represented with 1 over j omega C2. Likewise, moving to third arm, which is B and C, similar to the arm A and D, we only have one component, which is resistor, represented as R3. So total impedance of B and C, which is Z3, will be equal to R3. Now moving on to the fourth arm, which is C and D. In this arm, it consists of two components parallel to each other, C4 and R4. So as they are parallel to each other, and doing some simplification and having the equivalent resistance or the equivalent impedance, we obtain the total impedance Z4 as R4 over 1 plus j omega C4 R4. So, okay, now we will derive the equation for Schering bridge based on the balancing condition. So as we know that the balancing condition is given as the product of Z1 and Z4 should be equal to the product of Z2 and Z3. So upon substituting the values for each impedance, we obtain this equation, and taking the common factor, we will get this equation. And upon taking the j omega C1, which is this denominator to the left, to the right hand side, we will obtain this equation. And upon cancelling these two, we will be only left with this equation. When we multiply that numerator j omega c1 r1 plus 1 to the r4, we will obtain this equation. And then upon taking the numerator to the from the left hand side to the right hand side, we will obtain this equation. And at the right hand side, when we multiply this r3 c1 over c2 to inside the bracket, we will obtain this equation, so which will be j omega c1 r1 r4 plus r4 is equal to r3 c1 over c2 plus r3 c1 j omega c4 r4 over c2. So now, comparing the real and imaginary parts from the above equation, we will obtain the real part. So as of real part, we will obtain as r4 is equals to r3 times c1 over c2, and upon making the c1 as a subject, we will have the equation as c1 is equals to c2 times r4 over r3, which will be the equation number 1. And now, regarding the imaginary part, we have j omega c1 r1 r4 is equals to r3 c1 j omega c4 r4 over c2, and upon cancelling all the commons, we will be only left with the equation r1 is equals to r3 times c4 over c2, which will be the equation number 2. Now, in order to calculate the impedance angle for this Schering bridge, we know that the impedance angle is been given as tan theta is equals to 1 over omega c1 over c1 times r1. So upon substituting the equation 1 and 2 in the formula instead of c1 and r1, we will obtain the equation as tan theta is equals to 1 over omega c2 r4 r3 c4 divided by r3 times c2, and upon cancelling the commons out, we will obtain the final equation or the formula as tan theta is equals to 1 over omega c4 r4. So in order to find the angle, we need to take the tan to the right hand side. So upon taking the tan to the right hand side, we will have theta is equals to tan inverse of 1 over omega c4 r4, and that's the impedance angle for the Schering bridge. Now, regarding to the power factor, we have the formula for the power factor as cos theta is equals to r1 over r1 plus 1 over j omega c1, which can be also written as 1 over 1 plus 1 over j omega c1 r1. So upon substituting the equation 1 and 2 that we have above in the formula of power factor, we will have cos theta is equals to 1 over 1 plus 1 over j omega c4 and r4, and the quality factor, which is given as q is equals to 1 over omega c1 r1 is equals to, and upon substituting the equation 1 and 2 in the quality factor formula, we will have 1 over omega c4 r4. Likewise, the dissipation factor is represented as 1 over q, which is the quality factor, or we can say that it's the reciprocal of q factor. So upon taking the reciprocal of q factor, we will have the dissipation factor as omega c4 r4 for Schering bridge.